All right, what's up, everyone? We're back for another Ekkolápto Polymath Salon. This time, you may not find it on the Ekkolápto channel. You might find it on Jayanth, or Jay, as we call him, on his channel, which he will have linked up for people to subscribe to as he launches his community of people in theoretical neuroscience, theoretical computer science, brain-computer interfaces, cognitive augmentation. And that's actually part of why he's joining us today for this conversation on the questions of predictability and control of an intelligent system using probabilistic state transitions. So you're from UT Austin. You're a Texan, are you?
Yeah, Austin.
Yes. How do you like Austin?
Fantastic. The greatest city after Mysore. Yeah,
and I gotta rep. I have to rep Cambridge and Miami. I'm biased. But
yeah.
Austin definitely worth a trip. I understand you're starting a community, right?
Yeah. So it's
Want to give a little sneak peek what you're cooking up in the back?
So the idea is to have a BCI focused community in Austin that entails not just the academic and industrial R&D side of things, but also on the ethics side of things. Can we scientifically define and manage how BCI ethics evolve over time? So kind of these two strands is where I like to think is what's needed, and Austin can be that center moving forward.
Nice. So what we'll do right now is we'll go around, take a couple interests from people here, and then we'll go into your presentation. Yeah?
Yeah, sounds good.
All right. Mr. Ostroff, you first.
I'm a PhD physics student at FAU. I specialize in general relativity and complex systems, and I'm also an affiliate researcher at the Wolfram Institute and a member of the MPCR lab.
Hey, I do a lot in the innovation space and research. I'm a recent data science master's grad. I'm doing things with the radio management school as well at UC San Diego. I'm based in Boston and basically starting my own incubator and some consulting around innovations and startup and cool stuff like that.
Anudeep, if you want to give a quick intro.
Yeah, hi everyone. I'm a master's student at University of Texas at San Antonio. I'm doing my master's in computer engineering. I just saw the title in Luma and I was just super excited to know what it is. And I don't know anything about intelligent systems or something other, but what I do know is I have a background in computer science and know a little bit of probability, and I was just interested to know what's going on.
Perfect. I hope this can be something that opens the floodgates and you get even more and more interested in these sides of computing, because I think it's extremely fascinating. But thank you for joining. Morgan, we've met before.
Yeah, hi. My name's Morgan. I do psychiatric neuroimaging. I also am community manager for Neurotech X, and I lead neurotech development here at Frontier Tower in San Francisco. Very interested in the technical challenges around organoid intelligence. So really looking forward to this.
I have been hearing a lot about Frontier Tower in the last couple of weeks, like a lot. Well, we have to talk offline about this. I want to learn more.
But please.
And then Eli, last introduction.
I'm Eli. I guess I self-describe as a feral polymath on a journey to create a god. And it's maybe a couple billion steps away from that. But my current focus is primarily, I just build tech. I work at Transcend currently, making privacy enforcement tech, and doing a lot of various things everywhere, trying to make the world better.
There we go. That's what we like. I think that's a perfect segue into what Jay is working on at UT Austin. Yes, Jess, we will talk about Frontier. Jay, if you want to give again sort of a quick intro as to what you're interested in specifically in intelligent systems and computing, and then go into your presentation.
Sure. Yeah. First of all, thank you, and very nice to meet you, everyone. It's a pleasure. Hope to have this connection moving forward after this event as well. So yeah, a quick intro. I'm a PhD student here at UT Austin in electrical engineering. But my thesis work is more towards spatial memory and spatial navigation. So my day job, if you will, is I record from the hippocampus for rats while they do these spatial memory tasks. And I record from something called as the play cells. These are cells in the hippocampus that primarily encode a position in an environment. And so that discovery won about 10 years ago now, in 2014, the Nobel. So John O'Keefe won it for the play cells, and so my advisor's advisor, so like my academic grandparent, the Mosers in Norway, discovered another similar type of cells called the grid cells, which create these hexagonal grids whenever an animal, including us, are in an environment and we're trying to create a map of the world around us. So that's my day job, sort, trying to understand what's happening in the hippocampus when you have a normal brain, and what goes wrong when you have disease like Alzheimer's, because we do know that spatial navigation and memory is one of the first things that get damaged in Alzheimer's patients. So if we could figure that out, that would be something useful and important. So yeah, then the idea is that, okay, one aspect is you're trying to understand the brain for its own sake. It's a basic scientific question, perhaps one of the greatest. And then comes the engineering aspect, where like Feynman just said, if you cannot build something, you haven't understood it at all. So along those lines, so there is a thread of looking at the brain when an animal is moving around, us humans are doing some task, seeing what regions light up in the brain. Okay, that's one thing. But then you have the other aspect. Can you do something to the brain, stimulate at particular time points, and see, okay, what does that tell us about the function of the brain itself? So there are these kind of two ways of approaching this problem. And the second problem, if you think, is actually what BCIs do. BCIs in the community, let's say, have been mostly targeted towards, okay, you have a motor deficit, let's design a BCI that helps people walk, or you have more cognitive BCIs now, lets people get out of addiction, etc. Which is fantastic, which is very important. But then more fundamentally, under the hood is, okay, what is the extent, what is the ceiling of BCIs in general? How far can we push it? Is there a fundamental limitation that we might see moving forward when it comes to designing BCIs? So then naturally, one can ask a question. Okay, can we define something called as an ideal BCI? Imagine you had all the resources, like God level information of everything you need. So if you have that capability, then can you imagine the most ideal BCI that humans could design? And so then I got fascinated, and can we mathematically show that an ideal BCI should adhere to certain principles? And based on those principles, can we identify certain questions that as a field could pursue and answer moving forward? So this paper was the product of all these lines of thinking.
Rock and roll,
So-
like Ozzy Osbourne, R.I.P.
Oh yeah, no, RIP for sure. So for this question, we can identify a toy model, and then whatever insights we gain from that toy model, we can extrapolate extended towards human brains. So the premise is something like this. Okay, you have an organism, and that organism is in an environment, and it's in constant interaction with the environment. So there's like a two-way information flow happening, exchange. And you could define that the organism has a set of neurons. It has a nervous system, and the organism can change its body positions or any physiological signals. So you can define that external valve signal as the behavioral state. And the environment also acts on the organism. Think of it as like maybe the intensity of light right now in this room. That is the environment, and it's acting on me. And those, you can define that information state as well. But for the sake of argument, we're going to define the environmental state as a hidden, latent state. And we'll just focus on the neural and behavioral state. So this is like the premise. Okay, you define these two things. And then comes an important assumption or observation, if you will, that, okay, at any given time point and a spatial coordinate, can you exactly define what a neural and behavioral state the organism is in? Maybe not, because we know from the neuroscience knowledge research that it is tough to exactly pinpoint what state the brain is in or what state the brain is going to be 5 seconds from now. And you need a mathematical tool to describe these changes as well as the static states, and that's where probability comes. So imagine the organism has just 10 neurons, and you know the connections amongst all those 10 neurons. And you also assume that a neuron acts like a binary switch, can be 0 or 1. So you have a total number of 2 power 10 discrete neural states that the organism can have. And just for the sake of argument, you can pick 1,000 behavioral states. The idea here is these 2 power 10 neural states at any given time point will be associated with one of the 1,000 behavioral states. The reason why this discrepancy in the amount, the number matters is we know that we have about 100 billion neurons in the human brain and trillions of synapses. But over the lifetime of an individual, if you could create a behavior space of that human being, it wouldn't go to 1 trillion. Because even now we know that all the, let's say, Google, Meta, all the software companies kind of have a pretty good behavioral model based on the information one can gather through your usage of smartphones or computing devices. So there's this huge amount of information of an individual that can be gathered, and if you created a space out of it, that wouldn't be even comparable to 1 trillion, trillions of. So that was the basic idea. Okay, the brain can have a lot many states compared to the possible behaviors the organism can show. Given this assumption, at any time point, like I said, you have all the resources in the universe, so you can exactly look at what's happening in the brain and define a behavior state of the organism. So given that, you assign a probability value and will define it as a paired state, probability of a paired state. So that's like, again, we're setting things up. You can identify 2 aspects when you create a mapping of the sort. So you have, let's say, a matrix like this. You have neurons as the columns, time points as the rows. And at each time point, you associate the neural state with the behavior state. So one thing, you can identify uniqueness. This is again based off of an assumption, safe assumption of sorts, what we can gather. You have these specific modules in the brain that only mostly are associated with a function. For example, you have the fusiform face area here in the brain that mostly encodes faces. And like I said, my day job of looking at hippocampus, those cells have receptive fields only for certain contextual positions in the environment. So if you, in neuroscience, you have this concept of a receptive field where a neuron encodes only or mostly a specific functionality or in the environment. So you have this uniqueness going on in the brain. So there's one. And then redundancy. Because you have so many possible neural states and you have only a very less number of behavioral states, the brain does indeed use redundancy. And people, for reasons, good reasons, think that this might be an evolutionary mechanism of the brain trying to make sure that it's robust against any kind of damage. For example, think of all the plasticity that's happening. Classic cases of that Ramachandran explained. If you have a lesion in, let's say, the tongue region or the teeth region in the homunculus in the brain, there's a lesion or a damage, then the brain kind of creates these plasticities towards the foot or hand region. So if you touch your hand, then it feels like you're actually tasting, or yeah, your mouth is actually active if you touch the hand.
I have a thought on that actually, real quick, Jay.
Yeah.
One of the things I was thinking about with that, this whole idea of, it's sort of a way of saying you have distributed computers, right? I think it's not just the fact that they are, it's kind of like saying, don't put all your eggs in one basket in case, if it all happens in one thing, then you're screwed. But I think beyond just having things spread out and scattered, distributed to some level, I think the actual nature of the way it's distributed is also important. So we're saying, okay, we have these sort of redundancies to create robustness. But I think what's also important is how is it still connected while being separated from each other, right? Because, you don't just want the parts there. You want them connected in a specific way, coordinated in a certain way. That lets you have, I guess you could say, some kind of self-organization capability where, let's just say, one node fails because, you got an injury or something, and then it has enough of an instruction set to be able to rederive the lost structure, right? So this could also tie into things in how we recover data and cryptography. You guys know I've talked about the perceptual cryptography thing before. But I was just kind of drawing some lines and connections, pun intended, between this whole thing. Keep going.
Yeah. True. No, yeah, totally. And that kind of creates complexity when it comes to having the connectome of the organism as well. And that's why I wanted to keep it a bit simpler. That, okay, you need not know how regions are connected in the organism. If you could just look at these neurons as light bulbs and see these on and off states given a time resolution, even that's enough. Because when we move forward, I'll explain and try to put forward this argument that ideas from statistical mechanics can be very, very useful in mathematically formalizing the ideal BCM. But yeah, that's later. But yeah, no, good point. Yeah, so you define the uniqueness and redundancy now, and then comes the crucial, another crucial point. So we've been dealing with these static probabilities now. Then comes the transitions. Okay, T1, T2, T3. How are the states in the neural and the behavioral space changing? So you can define that. You can assign a probability value for the transition itself and create a matrix of these transition probability values. The crucial aspect here is if you observe, I'm creating these tables of sorts. So at a given time point, if I see a neural state, let's say, and I don't have access to the behavior, what the organism is doing or looking like, based on my previous observations of what happened when the organism was in the same state, I can assign a probability value that, okay, it's going to go to the state N2 from N1. And then create a probability table where the sum of all the probabilities, the 1024 potential probabilities, will sum to 1. And this is essentially a problem or a table that you get after sufficient learning, just looking at the organism moving and just looking at its brain, what's happening at a given time. So you can do the same with behavior, and then you can do the same with the paired state. Imagine, yeah, you have this God level power to look at both states at a high enough resolution with high accuracy. So you can design these probability tables. And this matters when we move forward. Why is a probability table unique compared to the state-of-the-art methods that the fields use, especially pattern recognition-based methods and Bayesian decoding? Bayesianism is a huge idea in the field even now, and people think of the brain as a Bayesian machine for good reasons. But when it comes to thinking of an ideal BCI, where are the loopholes? That was like the whole point of the paper, and we'll see that. So these things kind of corroborating again how states can transition in these spaces. So paired state, you can think of it as like this graph that's evolving in time. And now comes, okay, given these assumptions and given these given this mathematical base of sorts, can we define what an ideal BCI is? I haven't used the word BCI here because I wanted to keep it a bit more general without using the words brain and computer. So I say it as a prediction and perturbation machine. So, and this is the definition that we can come up with. And we can discuss some of those later on as well. That within an allowed temporal delay, the ideal BCI, that machine, should be able to observe both of these states at a good enough resolution, compute the transition probabilities and create those probability tables, and decide decision making. Should I stimulate or not stimulate to reach a certain destination of neural and behavioral state at a certain time point? So then if we define in this way, then we can actually look at, okay, mathematically, how does it look like? So let us say at a time bin TA, you observe the neural state NA and BA as the behavior state. So let us pick another time bin adjacent, the next time bin, and let those have these two states, NB and DB. So now, for a given machine, we'll define that it has a certain sampling rate that it can work at. It can be anything. Only the physical limits of the universe will be the limit for the sampling rate of the machine. So given these things, you can define delta MA, which would be the time required by the machine to detect the state actually. So this is a measurement problem inherently. The animal has a neural state at a certain time point, but your observing microscope, if you will take certain time to even register that it's a neural state. So that is the delta time. And we define that as delta NA. And then delta PA would be the time required by the computing part of the machine. So you've got the microscope, and then there's the computer that's going to create the probability table. And that takes time. It should run a certain number of clocks to compute that. So that would be delta PA. And then you have delta TPA, which would be the time required by the machine to create the transition graph. So if you remember, delta PA is just to create that static probability table. Delta TPA would be to create a state transition graph such that it ends at a certain time point that the user has defined. Maybe, for example, 20 time steps. What's the likelihood of the system being in a certain neural and behavioral state 20 time bends from now? Then you create the transition graph until we reach that 20 time bends. So that would be delta TPA would be the time taken by the machine to calculate this graph. And then you have delta DA, that the computer, the time taken by the computer to decide, okay, now I see this neural and behavior state, and the user or the objective function that I've been trained on says that I should make this organism reach a certain neural and behavioral state. So if I do not stimulate, will it have a higher likelihood of achieving that state? Or if I do stimulate, how do I stimulate to get it into that destined position? And that takes some time. So this, you can think of it as the decision-making time. And then delta SA is the final part. Okay, now the system has decided, and let's say it has to stimulate the organism. And that takes a bit of time. Just like you had the measurement problem of that time delay of getting the ground truth of the organism state, you have it the other way as well. Okay, you need some time to affect the organism.
I was gonna say the time delay thing is pretty interesting. So on I think it's actually tomorrow. Yeah, tomorrow we have a Ekkolápto researcher who's gonna be talking about self-organization in time, temporal emergence, which is, I guess those are fancy ways of talking about some of the things that you were just mentioning about this delay problem. Because we always think about how do we connect things spatially, right? You know, when you're building something, you're thinking about how do you connect things spatially, but we don't necessarily think about how do you stitch together continuity and connect things in time. And one of the most fascinating things about, you know, if you're trying to aim for efficiency, what you're basically saying is you're trying to rearrange space to get more done in time, right? So if you're designing an engine, right, for instance, just by reconnecting the parts differently and even removing some parts sometimes, you can actually get it to do more in time. Like your economic, which is also something we're having someone who's sort of a complex systems and economics cognition science type researcher. His name is Benjamin Lyons, also on Sunday joining the salon. So I guess everything's kind of getting roped together. But
Nice. Yeah.
my point with this was that it's very interesting to think about how things sync up in time. Right? We have a lot of, I feel like it's sometimes easier to talk about how things connect, coordinate, integrate spatially, but not as much temporally. And the delay issue that you're describing, I think that's applicable to a lot of systems, which we can talk about later.
True.
Yeah.
So, you know, time is, I think, time is underrated. Let's put it that way. We mostly think of computing in space. I have this was a recent preprint just published, put on this week. But yeah, we can talk about that, where I explore some of these issues in terms of the retina. How is the retina computing when it's shown in image, and can we arrive at certain fundamental uncertainties that will have effects, the the downstream networks of the brain. But yeah, that's a whole different issue. But yeah, so given these delays that you can define, then you can mathematically frame how an ideal BCI should look like, or what is that fundamental inequality that the ideal BCI should adhere to. And this is that inequality. So what this is in simple terms trying to say is you need to do all of these measurements, computations, and stimulations before the machine does any measurement and computations in the next time bit. Because this has fascinating consequences. If you think about the brain as a dynamical system, and since our birth, we are moving in this very high dimensional space, transitioning from point to point. Whatever underrated or small decisions or perceptions we might have had a few days ago, a few minutes ago, a few years ago, will be consequential for what you do and think and act in future. Basically, if someone had an ideal BCI or a BCI that was close to this ideal BCI, it matters a lot that you do not stimulate or do not take decisions on stimulation just based purely on a few assumptions that, okay, the motor cortex, oh, if I can stimulate here, there's a damage that I cannot move my hands. So let me stimulate the motor cortex, the hand region, and do that. But we do not know how a particular kind of perturbation in the motor cortex will affect the surrounding cortical regions, will affect the prefrontal cortex, for example, will affect the hippocampus, just down in the brain. So this is aiming towards that. This will have might potentially have ethical repercussions as well, because what you claim with a BCI or how you gauge the quality of a BCI will be based off of this inequality. Where is this new BCI lying on the spectrum? These parameters, if you will, the space of these parameters. So yeah, those I also mentioned how. So this is what I was talking about, a potential ethical issue, because it's a dynamical system. Let's say you are stimulating the visual cortex because your vision is not proper. But we do know there are feedback connections between the visual cortex and the prefrontal cortex and the orbitofrontal cortex. These are decision-making regions. So if you keep constantly stimulating the visual cortex, just because your vision is getting better, it can have adverse effects on how you decide on things, how your habits are formed. Because the connectivity graph, the anatomy has one constraint, fundamental constraint, and this whole idea that your brain as a network is moving through these points as a dynamical system. So if you keep stimulating one region for the sake of one functionality, the other region can reach an attractor basin, which might be tough to come out of. So unless we know all these parameters properly, it's dangerous, or it's not safe to claim something with the BCI. So that's I think the meat of the paper. One of the reviewers wanted to say, okay, where is the noise here? Where's the noise issue? Because noise is a huge theme, research theme by itself in the field of neuroscience. Because traditionally, people in computational and theoretical neuroscience came from the background of engineering. And engineers love the idea of control systems. Okay, you have a transforming function and some input goes in, and there is this communication channel. You put in noise, and how does this input and noise affect the output? But that control system perspective cannot work for long, because how do you define what is noise in the brain? Just because a receptive field in the visual cortex is not showing this clean peak when a red colored blob is in your left eye field, that doesn't mean that there is noise inside the brain that's making this neuron not have that peak for that red blob. Maybe that particular neuron is part of this whole conglomeration of neurons that is encoding that red blob space. So it's more of a collective population code. So when you get into these population representations, noise kind of becomes meaningless. So that's why I kind of put a small section. And then this T metric is something that becomes a natural product of the ideal BCI that we just defined. Because remember, I assumed there that as a user or as the observer, you get to define the temporal resolution at which the machine is working at. And you also set to define the sampling rate. But even then, if you had all the resources in the universe to have the best temporal resolution and sampling rate, is there a fundamental physical limit on what you can do with it in terms of affecting the organism? And it seems like there is. And this straight away comes out of the inequality that I showed before. So on the y-axis here, we're seeing accuracy and computability trade-off. Accuracy is more like, okay, I see this neural state now with very high accuracy. Let's say for number's sake, 95% accuracy, this N1 state will reach N9 state in exactly 5 time bits. So you assign a very high probability value that this state transition will happen, traversing a certain path in the transition probability graph. But in order to get at that probability value itself, what about the computation that's required? Because there is a fundamental limit on how much you can compute in any given patch of space and duration of time in the universe, right? So there is a fundamental physical limit there. So computability then becomes another fundamental bound. And this trade-off is essentially the ratio of computability and accuracy, and that you can define as T metric. So what this essentially is saying is, even for an ideal BCI, you need to be in the right sampling rate regime of the machine at the expense of accuracy, such that you can reliably compute properly and still affect the organism. And that is this blue rectangle that you see here. And as you move away, yeah.
I was going to say, this reminds me of a couple of things. There's this sort of thing I talk about, the optimal distribution, hormesis, and dose responses, which we can get into later. But for some of the Wolfram people on the stream to think about, I see some potential connections between this and computational irreducibility. If that's put up any connections, yeah.
Yeah, true. No, definitely. I think that, yeah, there are a lot of connections. I think we will need the tools and techniques in computational complexity theory for any extensions of this work for sure. So then, kind of stopped, paused at defining this T metric because we're still working on it right now, on how to create simulations using a very simple recurrent neural network. And can we define, um, parameterize, put a number on these T metric and the delays while the RNN is running on a very simple task like an agent moving in an environment, a square grid. Um, so that's more of the computational side of things that's still ongoing. So this was like the meat of this paper was to lay the theoretical foundations for this whole kind of theme of research. So after that, I decided, okay, it's important that the field out of this can identify certain questions to pursue, so that it can be a collective effort that people can pick and choose certain questions and explore, see what's happening. And for that reason, I kind of lay out 8 open questions that naturally fall out of this theoretical framework. So, for example, I don't know if we have enough time to go over all 8 questions, but I can maybe pick and choose.
Pick and choose your most thought-provoking ones.
Yeah, what excites me the most is the current kind of revolution happening in neuroscience, systems neuroscience. We have these incredible measurement tools that you can record from hundred thousands of neurons at a time. And using optogenetics, you can pinpoint a neuron and turn it off and on. So given this a really privileged position, that wasn't the case even 20 years ago. And a recent fact that we have an organism called C. elegans, and it has only 302 neurons. And the entire nervous system, the connectome, if you will, of that organism has been mapped out. And this happened about 34 years ago. But now recently, we can actually perform these assembly line kind of experiments where you have thousands of these C. elegans worms. So these are basically worms, that they are like centimeters long or even millimeters sometimes. So what you can do is, right now we can have thousands of these worms lying on a petri dish, and with each worm you can use imaging, specifically fluorescence imaging, calcium imaging, and even sometimes voltage imaging, and see which neurons are turning on and off. It's like 302 light bulbs of different colors switching on and off, if you can imagine. So we have an experimental system to test all these theoretical, the mathematical constraints that I just laid out. So you can get the T metric, look at how the probability tables look like, get the state transition graph. And with optogenetics, you essentially have the whole BCI. So then you can actually get values, actual values from experiments for each of these delays, and see, okay, how much can we push forward? How is this C. elegans dynamical system changing in time? What do the perturbations do for this organism? How is the synaptic plasticity changing because you perturbed specific neurons for a long period of time? And just showing these things in this model organism can have important implications on what we even do with human BCIs. Because if we show that, okay, with this organism of 302 neurons, there are actually attractive basins forming in a far distant part of the network, then what does it mean that, or what does it even mean when you think of BCIs doing the same with the human brain? So it's exciting, and so that's the main part. And at the end, I kind of compare this whole framework with the existing state-of-the-art frameworks used in neuroscience and neurotechnology. So one classic approach, the most standard approach, is Bayesian decoding. And how is this different from standard Bayesian decoding? The key part is this. With Bayesian probability distributions that you get, there's no notion of causality, if you think about it. It just gives you a conditional probability. Okay, given the neural state NB, okay, there is this conditional probability for NA. But with the state transition graph that I showed, there is a sense of direction. You can actually assign an activity vector that has a direction and a magnitude, which you cannot get from Bayesian, present-day Bayesian decoding. Potentially, it will need, we can have some close connections with what Udaya Pearl talks about in his do calculus, where you actually have the causality included in the standard Bayesian approach. And people will do that with Bayesian networks. So there might be close mathematical similarities between the two, but that needs further exploration. Now, what about standard pattern recognition methods? Think of fMRI. That's what people do. Humans are shown a particular image, or they're asked to do a certain task, and then they look at these patterns in the brain, and then they just say, oh yeah, this pattern is correlating mostly with this behavior. So then, okay, there is a specific pattern in the back of the brain when the person sees faces as opposed to objects like cars and trucks. So then that must be a functional module for face encoding it then. You discovered the fusiform face area. But you see, again, the problem of causality occurs here. But we do want to mention that pattern recognition is the first work, first step in getting the state transition graph. So in that regard, it is a part of the present framework, but it's not the complete picture. And then, yeah, so then these two approaches are more like data scientific approaches. Like, okay, you have these probabilities that you've gathered. Can you make sense of it in a simple, meaningful way? So then you could use these dimensionality reduction techniques and so forth. By themselves, they are not. They are just a part, but by themselves, they're not the whole picture when it comes to the ideal machine that we talked about. And I think with that, yeah, I think that's it. That was the whole paper in a nutshell. Thanks, everyone. I hope it wasn't boring. Tried my best.
Nah, man, you're good. You did great. I think I cut off for a second. No, it was good, and I like that. I like that this was pretty technical and went wide ranging. DVZ got a question, so I think what we can get started with then is, and it's a shame Dugan had to leave because I had some interesting things about this nature of computational irreducibility and all that, right? But in addition to that, there's something interesting that happens where, okay, let's just say you have this this distributed system, right? Why is it, I guess you can at least say this in sort of biological systems, right? Where if you induce a damage, like you can stimulate it in such a way where it creates this, you could say an attractor basin. All right, so one of the ways that you can really get something to bring other things to it, right, is, if you damage your bones slightly or your skin, what happens? A bunch of resources start flooding to it, right? And there's something about the nature of, this ties into the hormesis thing, Mr. Ostroff, that we talk about, where creating a loss of information in a specific kind of pattern can induce not just a recovery of that, but like an over recovery, an overcompensation. And it's also, even if you just sort of think perceptual, like perceptual attractor basins, like think of just what attracts your attention, right? I think, this ties into the whole perceptual cryptography thing. I think this also ties into the way we will physically and perceptually interact with our BCIs, which I'll tie this into. And again, anybody feel free if you want to chime in with any comments, ideas, questions, because those of you who are return guests know that when I start talking, I don't stop. So just feel free to hop in. But what's kind of interesting perceptually with attention and attractor basins, right, is, okay, we sort of say that something is attractive. There's a face, there's this sort of physical representation of a living system that we call a face, or a body, or these clothes, or whatever, that can be so attractive where you can be completely just like locked in on it, right? It's also, this is also a thing that happens when you see something that doesn't match up with your expectations of context, right? Like, let's just say you're in the office or something, and then you kind of notice that something is off. That noticing is the thing that attracts you. You're like, wait a minute, something is kind of off. So there's sort of these attentional, perceptual, attractor basins, attractor states. And I think that the weird thing is that you can sort of see this in multiple levels across the organization. I think you can say this is how cells integrate and connect with each other. In one way, when you talk about how, we talked earlier about self-organization, spatial continuity, temporal continuity, how do things maintain an attractor state in time? What properties, can you coordinate in time that create an attractor state, an attractor basin? And I think one of the ways this ties into BCIs, I know I've jumped around a little bit, but one of the ways I think it connects to BCIs is that there's this thing that I've noticed when I've done a lot of cognitive experimentation myself, right? Is that if you're trying to remember something, right? If you know that you're supposed to remember something, like I'm supposed to remember to do something at, say, 2 o'clock today kind of thing, that only works if I'm coordinated and connected with the system that's always kind of there and active. It's sort of like I can rely on my notepad for memory, for reminding something. But if I lose my notepad, then I'm screwed. And I think this ties also into the nature of communication, because what are you doing when you have a BCI? Is this some kind of biochemical, bioelectrical kind of conversation that the cells are having that lets you have communication at a greater scale that we'd call, normal human, natural language? We can store thoughts in it. It can influence other aspects of our nervous system. I think we should sort of be examining the way electrical systems integrate with chemical systems, at least in brains, for BCIs. And we should also consider how brains will adapt to the BCI. Because one of my sort of biggest things that I've always thought about, again, this is one of those things in the realm of science fiction, but it could be real, is what does a biological Neuralink look like? What if you could take a BCI that you normally have to go and do all this stuff for, but there is a way to grow it and induce it in your mind? There is a way for biology, which already sort of taps into electricity and electromagnetism and everything to a degree. Is there a way you can get that at a greater scale where, as long as other people have that, you can also communicate using this biological Neuralink? I'm curious if any of you have thought about this kind of thing before.
I will say there is something called, I don't know if you've heard of optogenetics, where you modify organisms' DNA and you set it up so that when you shine a ray of X-ray light at it, because that can penetrate the brain, it has a certain kind of response. So like I saw an example where someone made it so that they had a mouse that got really angry every time they shone light at a certain part of the brain. And there's also the closest thing to like a biological Neuralink would be there's also chemogenetics, where you're doing similar things with sort of chemical processes, and you say, okay, well, I know if they ingest or I inject this chemical here, it's going to go here, and it's going to activate this sort of programmed DNA, that kind of thing. There's
Yeah.
also radiogenetics, by the way. There's a whole world, and there's the radiogenetics are cool because that means you can use sound signals, but sound signals that the organism is unaware of consciously.
I will say that the sound one is kind of at least on the depths of the internet that I scour through. There's various phases of this the sound is sound influencing biology. So I think there's some things that are a little on the woo side, but I think there are interesting ideas about how the nature of sound can entrain biological systems. In fact, I just had a conversation with somebody about this earlier in the day. And what does like a biological instrument look like? We can use these sort of very physically engineered things that we call a guitar or a drum set to entrain patterns in our brain in a certain way. Yeah, Jess, entrainment is a key concept. Exactly. And I think if you look at sort of more diverse forms of entrainment, what you were saying earlier about the time delay thing is I would say entrainment is one of the ways to solve that. Right. So
that's, yeah. How can you expand on that? How could entrainment solve the time delay issue?
Well, we're actually gonna get more into this on this would be tomorrow's salon, the self-organization and time one. But one of the things that happens, right, is if you have things going at a different pace from each other, what is the kind of substrate or network that connects those things, right? So have you ever seen a bunch of let's say musicians, right? And they're improvising, and maybe some of them scour off and too far off the typical BPM or the rhythm or whatever. What's that process of how everything comes back into sync, right? And there's this sort of very famous example in complex systems, which I'm sure many of you have heard of before. It's the metronomes on the wooden board or whatever, and if you put it on, eventually, if they're out of sync, again, this is patterns in time, not patterns in space. It's important that we're talking about the pattern in time, right? It's behavior in time, right? So it's kind of going off, and there's something about connecting it through some substrate that it's able to almost send feedback to each other and even itself out. But what also sometimes people don't talk about is that it can go out of sync again, right? And I think there's things that look like they're locally patterned and, they've reached some kind of homeostasis, but that's locally in space and locally in time. I think there's a lot of things that look like they're patterned locally in time, but maybe if you zoom out, they don't so much so look the case, but then also vice versa. And then real quick, Jess, before I get to that, to answer your question, Jay, I think we should look at ways that we already try to entrain our minds with other minds, right? Which would be things like music and language, and see if we can bring over some of the modeling systems from how we do that and things like music or whatever into how you can get a BCI to sync up better with your brain. Because it's sort of like, if you're playing an instrument, you don't want to keep checking with the other person, are you in the correct key or are you in the correct BPM? It should be as automatic as possible, right? When you're in a sports team, if you're not sharing a sense of, a shared sense of time, right, of pacing, of synchronization across the field, doing all these different things, then it might be a little hard to make that goal. And really, this is just a complicated way of me saying, are there ways we can borrow principles studying, behavioral dynamics in, say, sports and music and the way systems sync up with each other, and then just, shrinking it down to what happens in the brain? That's my comment.
True. I think that will definitely push how BCIs are designed. Using, for example, let's say we know that there is a rhythmic entrainment between distant regions of the brain, like the temporal parietal regions and the frontal regions, maybe gamma, theta gamma coupling. But there are rhythms that in a split second, even that any physical device can even dream of achieving that speed. They kind of get entrained when the animal needs to decide if it should go left or right. So rhythms are being used to perform these computations in time. And that's a very key missing piece that we're not thinking it for sure.
As you were saying earlier, time is underrated.
Yeah.
Jess, you want to go next?
Yeah.
Perfect.
And I was basically going to do a kind of a +1 to things that Addie was saying, but also kind of the I won't say top theme, but one of the major themes that all these salons kind of come back to, and the sort of the stepping in and out of developmental stages, and like the path or developmental dependency. I was going to go all the way back to like classic developmental biology, and I think we all know this, but just to kind of center the discussion here, like as a embryo is developing, as a brain, as a fetus, whatever is developing, there's certain things that just cannot possibly come online until certain maturity has taken place, and then certain entrainment or coordination of the organism as a whole takes place. Like there's reasons why the sequence, yes, organizing around time, and then the sequence of development are like very key things. So I think a lot of what we're getting at in Ekkolápto is sort of this. I've been saying the word like teleological coordination lately, and I'm kind of trying to write something about that and talk about everything else. But at the very least, the temporal coordination, the developmental coordination, and in terms of getting toward like a BCI that's biologically based, I think one of it kind of centers this issue that we're talking about of how would it do the coordination of it, and these kind of associated questions of where in the development of the organism or the mind or whatever would it come online, because like at a couple weeks old, you're not going to be um, doing the same kind of physiological interfacing. Like what is interoception at that age is a different thing than 1 year, 2 years, 10 years old. So where in those processes do these things like these tools of coordination or these like BCI things that allow you to interface differently, where did that come into? So that's a broad tangential comment, but I always keep thinking about these sort of the stepping in and out of the kind of the classic Ekkolápto hormesis perturbance, stepping in and out of the okay, once we're engaging this level, we go in depth, we have less nuance here but more specificity, and then stepping back out. And I think there's the sort of the macro developmental aspect of where can some of these changes take place as an organism or other entity in its developmental process. Yeah.
True, that makes sense. Yeah, that kind of, you can also tie that into what I was talking about in terms of learning. You need to learn to create these probability tables. Okay, what is the starting point of learning? Are you gonna start looking at the neural and behavioral stage right after the birth of the organism? Right? Because what if those initial conditions matter? These specific crucial stages in development matter. Those are open questions. Yeah, fascinating. This kind of ties into what Jesse was mentioning about development. This question 6. So if you remember that we defined T metric for an organism, it seems like that T metric should change from organism from species to the kind, because for example, the T metric of a C. elegans need not be the same as for a rat or a monkey or human. So there is that organism-based difference. But the key part here is it seems like the T metric can be defined for an entire species in general, because we know the whole field of neuroscience works, does what it does, because if we record and interpret something that the brain is doing with two animals, let's say two monkeys, the whole point is that the rest of the monkeys are also using these principles when it comes to, let's say, decision making or some functionality that's correlated with the brain state. Considering that, it seems like this T metric can be defined for species in general. But then the problem, an important question comes forward. Okay, now you know T metric for an organism, but how did you define it? Did you start training the prediction machine, when the organism was 5 years old, and you left it for 5 years to run, and then the 11th year you can do these predictions and perturbations, you can create these probability tables and state transition graphs, and then you might realize, okay, it works for a few years, but then when the organism is left out of its natural habitat, it goes to a different habitat, all this whole mapping is changed, and you need to learn again, learn the mapping again, and create these tables and graphs again. So would it have helped if you instead started to have this BCI organism interface right after the organism was born, the first year, so that you could have picked up certain developmental changes in this functional mapping before? So that is, yeah, an open question that needs exploration.
Yeah, I've got a couple questions.
Go
One
for it.
on sort of the planned experimental approach and one on the basic idea here. Are you, I know a big deal in this sort of computing behavior from neuronal states is polysemanticity, where two neuronal states can look extremely, extremely similar. Maybe, the difference in sort of neurons that are lit up, I could count on one hand, but they actually mean very different things. And this is because of sort of the fact that neurons are sort of computational objects, and they're, you can have small changes that result in completely different behaviors. I'm curious if your sort of approach accounts for polysemanticity, or if it's sort of like a one-to-one type of thing.
Both, in a way, because right in the beginning, when we define that there's this mapping between these two spaces, neural and behavioral space, you can account for the uniqueness and redundancy. And all of it is dependent on the number of behavior states, for example, that you define for an organism. To give a specific example, let's say you have C. elegans worm, and there are two neural states, distinct neural states, that encode two positions. But the thing is, the positions themselves are the orientation of the tail of the worm. And so you can define it in terms of angle. But the problem is the difference between the angle, the orientation angle between the two states might be 0.05 degrees. I'm just saying a number. Trying to make the point that it all depends on how the user defines the behavior states and creates the space of behaviors. You can lump those two behavior states together and call it one, then you'll have the redundancy, or you can separate them out and call it, okay, these are two distinct states, and it's a one-to-one mapping.
I guess I get what you're saying, but I guess what I'm talking about is less multiple neural states mapping to the same behavioral state, at least when you've coarse grained it. So like you said, I might coarse grain it so that that tiny difference doesn't really matter to me. But what I'm talking about is the same neural state, or seemingly the same neural state, as sort of as measured by imperfect instruments, mapping to separate behavioral states.
Yeah. You also,
and it's sort of an issue you get with polysemanticity in neurons.
True. So you will incorporate that by extension when you create these probability tables.
Okay.
Does that make sense? Because let's say you had state N1 encoding a behavior state B1, and you observe that 10 times, but something happened, changed while the animal was traversing this space, this dynamic system, or something changed with the environment. So it's a latent state, not encoding that here. That made N1 actually encode a behavior state B4. But then you're going to incorporate that in the probability table, because that decreases the probability of association. So moving forward.
This is very brilliant. I like this way of approaching it. Sorry if you already stated this. Like I said, I came in late.
No.
I'm super fascinated by this work, and I think this kind of work is really needed in functional neuroimaging, because it's there's a really famous paper called "Functional Neuroimaging is Modern Phrenology." You may have heard of it, but
I've seen this. Yeah.
So this kind of thinking that gets away from sort of it kind of looks like this, and I guess that means this, and defines things more mathematically is really needed. This is really brilliant.
All right, cool. All right, well, let me finish then with one kind of lasting thought on this. There are multiple sides to how I kind of think about problems like this, and I guess the first thing is, okay, what are the reasons why we want to have a BCI? Why is it that the current way that we're kind of trying to make BCIs has the limitations it does, right? And what I wonder is, are cognitive systems just better ways of trying to coordinate with the environment? And if we sort of come down to brass tacks, that maybe that's actually what we're trying to do with this thing that we call cognition, is we're trying to find these, when I say that we're trying to coordinate with the environment, I have to also emphasize that that doesn't mean you become one or the same with the environment per se. I think there's a thing that happens when people talk about connecting and bonding and integration, where people will talk about, we want everything to be connected. And it's like, well, what do you mean by connection, and in what way? Because there's this film recently, actually, I saw, it's called Together. It's sort of I won't spoil it, but it's sort of a mix of I guess a comedy and a horror in a strange way. And it sort of deals with the nature of over-connection in this very artsy way. But the sort of scientific perspective on that is, you don't just want to take, two things of Plato and mix them together, right? I always say with the integration thing that, if you want to have a V12 engine, you don't just take two V6 engines from a Toyota or something and just mash them together, right? You're technically combining them, but it's the criteria and the filters that you're putting in place that create the shape of the connection and all that. And what I think is interesting is to better build a coordination system with the environment, so that we don't become one with the environment, but we're able to communicate with the environment better and understand it. When we talk about understanding the laws of physics and all these things, we're trying to better communicate with, this sounds like a very Yoshibok thing to say, but we're trying to communicate with reality, right? We're trying to understand the language of reality or whatever through this thing that we call mathematics. And if that's part of the reason about why we're having these BCI things, right? These sorts of ways of augmenting cognition and experience, to better understand the world inside and outside of us, and to almost have some control of it, is I think we need to be looking at the less conventional ways systems will sync up and coordinate with each other. I have this one kind of thing that I'm building on. I'm not necessarily quite ready to do a full presentation on it. But Jay, for your situation about how we create BCIs, would you essentially say that we're trying to connect the brain, which could be thought of as a more intelligent, more agential system, with a lesser intelligent and lesser agential system. Now, I don't mean this in a negative way, but I think, you know, if you think of the brain on its own versus the BCI on its own, I'd say one is a bit more capable than the other. But why is it that you can take, you know, this collection of metals a lot of times? You know, I say computers are magic rocks, they're magic minerals. There's some way to connect all those particles and everything that you get this thing that you call a computer, so that we can have pixels, we can have ways of controlling electricity and magnetism. And from a philosophical perspective, Jay, and since I'm just kind of going on, right, is there something to the perspective that you can gain a skill and an understanding of a system and control by communicating with a system that's foreign to you as the observer? And I can give one analogy to this. I've had conversations with people that have, let's just say, language barriers, where they come from extremely different fields. And then sometimes they're perfectly smart people, well-intentioned, but there's this kind of language barrier, or like a context barrier, where things don't properly connect up, right? Like the wires are just missing each other. And there's an interesting that I've noticed, where when you try to engage with these kinds of discussions, is that for you to be able to have different systems in your brain communicate with each other, it should feel like you're talking to yourself. I think one of the reasons a really good team can work and a discussion can work is that there's enough coordination between the participants where it feels like you can just talk to yourself. Like in these kinds of conversations, a lot of times I can talk the way I talk to myself in my head to everyone here, because there's this sort of established language that we all share, an established context, right? And I think one of the ways to think about how a biological system like a brain will adapt to, you know, either a, you know, invasively or non-invasively implant AI. Yes, Jess, going back to old school cybernetics, your favorite, is the experience of a good augmentation system is that you should be able to gain more by still feeling like you haven't changed. You should still be able to feel like you're talking to yourself and doing things in the way that you are, but now you're tapping into something else through this tool. I guess that's a very scattered way of what I was saying. Curious if that gave anyone ideas or questions.
Thanks again for the presentation. I don't have direct comments, but it definitely made me think of some recent presentations that I've seen. One from Max Canwell, who is also doing theoretical neuroscience in this way, and kind of assuming an ideal recording system, and is coming from a background of kind of information theoretic analysis of Boltzmann networks and things like that. So I think there might be something interesting there, but when also looking at these kinds of systems, it just also reminded me of Haran Naibi's presentation on game theoretic analysis for AI alignment, and again, kind of assuming these ideal conditions and dealing with the same probabilistic, in this case, two probabilistic agents, which I wonder if you could expand this idea to be having the BCI case, where we're trying to exchange information to fully understand the other, to better understand the other agent. And I think that's what you see in some of his analysis. And yeah, so certainly thought-provoking, and you know, love to share those references with you. And
Love to. Yeah.
But thanks again.
Thank you. Yeah.
Thanks, Morgan. Yeah, you guys should totally connect.
Yeah, definitely. Love to.
Cool. And I think Jess has his hand raised one more time. Jesse. No.
Sorry, I was from before, but yeah, I mean, what you said before, Addy, was like very, you know, every good regulator theorem in the sense of the best, well, not the classic phrase, the best model of a cat is another cat, preferably the same one, but meaning like, you know, the coordination across them. But regulator is specifically about being able to account for all the other states. Like if you're going to have something that regulates or understands, which is this an interesting way to think about it, sort of intimacy, which is not a cybernetics concept, but kind of what you're getting at is the sort of intimacy or cultivated shared understanding between agents or in a system, for example. But at a cybernetics level, it's, can the regulator system or agent account for all of the individual states within the thing it is regulating. And I think an applied sense of what you're talking about in terms of like the coordination, teams coordination sense and so on, would be maybe like in a sports team analogy, which is a good one that comes up often here, is not just there's not maybe one regulator dictating everybody else. You could say that's what the coach is doing, but at a higher level, that's not really what a coach is doing. Maybe what a coach is doing is just offering facilitating a unified framework or lens or vantage point. But within that, there's sort of this developed, there's a developed intimacy and familiarity in that state where all the agents in this artificially constructed, arena have the ability to understand what the other entities are doing because of the way it's set up. You're creating this minimized you're playing the game, you're doing the game, so you're in that space,
Right.
and I think that ties to a lot of another tangential comment to throw in before we leave, and I'm gonna look at what DBZ said there, is sort of along the lines of in my, I guess, one of my home labs, the orthogonal lab, like we've had a in terms of cybernetics and stuff and whatever else, like sort of a meta brain approach, which is like having a more interested, more in-depth regulator, like the brain, but then regulating this body, and like very Lisa Feldman Barrett takes on cybernetics and brains, and that like you have this brain inside of a body, and the body's, the brain has no direct contact with the world, so it has to figure out how to manipulate this body and controlling this entity as it's engaging in the environment. All that kind of stuff I think is interesting. And yeah, I'm seeing the comments about computational intimacy. I don't think it's a real thing. I'm just sort of augmenting, I'm kind of applying every good regulator theory to what we're talking about here and coming up with that. And it would definitely be interesting to talk more about that too. So yeah.
I was going to chime in, Jay, unless you have something you want to say in response.
I think they're fascinating questions for sure. A lot of space.
A lot to marinate.
Yeah. A lot of
Yeah. Computational marination. What's if you could model the marination process and fermentation process computationally, I have an idea on that. But just a sort of more direct response to the coaching thing. And this will also be covered very heavily tomorrow. So I highly encourage everyone to join for the self-organization salon tomorrow. I think it's at like 2:00 or something like that. What's interesting is that you can have a coaching system, an instructional system that is not centralized, right? It's you can have it you can have little packets and slices almost. Now again, DBZ, think of the Michael Levin planaria worm thing. Those of you who are familiar with that, right, and how the worms will kind of regenerate, right? Is that you can have the thing split in all these pieces, and you don't need to necessarily have, for people to eventually get to, something that sounds like an orchestra or plays like a sports team. You don't need to necessarily have the centralized coach or the composer. You don't need to necessarily have that. You can sort of achieve that through the means of self-organization. Right? Like what I was saying earlier with improvising musicians, for instance, is that, you're kind of playing, testing things out, improvising on the fly. And as long as you're in a contained space, which again goes to that whole integration connection thing, is that there's something about that process that then lets you start to sync up with people like the metronomes on the wooden board, right? It's sort of like that. And the key then now, right, is one of the things that happens on the if we go with the analogy of the metronomes on the board, is okay, then they're just all doing the same thing, And if you think about what, complex dynamics actually are in music, whether it's melodies and polyrhythms or sports or whatever, is you don't actually want everything to necessarily be syncing at the same rate, but you sort of want a polyrhythm, like they're inherently connected somewhere else, but then they're also able to explore different territories and still be connected. Right? If you think of what makes a good song, it's not the same thing in both axes, right? You're doing different things in time, and you have different things happening together in space that we call, multiple, rhythms at the same time. You have the keys, the piano, the drums, all these different things, right? And it's the way that they're tracking throughout time, but they're doing that by being different, right? They're still synced with each other, right? You don't want to play something too offbeat, but if you put something offbeat in a specific way, we just call that a polyrhythm, right? And that's also what happens in, say, things like, sports teams, is that, yeah, there's physically different people, physically different bodies and minds and backgrounds and everything, and they're going and exploring all these different paths, right? And yet they're still synced up enough with each other where they can reach a goal, right, without necessarily, telepathically communicating with each other in real time, in a sense. And they can still reach this very difficult goal that's beneficial for everyone. What is this, Jess, that you're saying here?
Yeah.
Curious on that one. Any thoughts?
Yeah, I mean, I would just, that's the classic like birth and information thing, and generic, like the classical models of complex systems, where it's not like every individual part is doing the thing. It's what you said, yeah. And then I was responding to Morgan too. So yeah, it's good.
All right, thank you, Jay, for this wonderful presentation.
Thank you, everyone. Lovely to meet you.
Yes.
You want to tell anybody where they can find you now? Maybe X and a
YouTube
channel?
So yeah, put the email. Let me put another one as well. Yeah. So one is the U Texas, one is Gmail. So either one. I'll keep looking. Sorry.
And I understand you're putting together a YouTube channel as well.
Hopefully.
Yes, hopefully. Let's do that sooner rather than later. But
yeah.
Tell everyone a little bit more about the community you want to build in Austin for augmentation.
So
DCI.
yeah, so the first thing, in fact, is I and another faculty member here in the neuroscience department want to have an extramural postdoctoral researcher series who are working in the neuroscience, neurotech space, and who are about to go to faculty positions. Mainly inside the United States. And the point being, okay, if we could have these rising stars that we can imagine in neurotech, and if we could have connections, create a community of them with the industrial DCI people. So moving forward, we'll have this whole community set up. So who knows, maybe some of those postdocs can go on and create their own startups, DCI. So there should be this back and forth communication happening between academia and industry, and so that's the first thing that we're looking at creating, hopefully. Yeah.
I agree with that. I'm doing a lot in this space between trying to do some of the coordinated work between having people get off the ground of like certain niche or incubator type projects. So more on that later, but I definitely I'm sympathetic to the cause.
Cool. All right. This is a wonderful time. But before everyone leaves, just one more thing. We have an incredibly special event that is happening at MIT Media Lab on August 23rd. I'm fortunate to be helping organize the Human Augmentation Summit. Once again, August 23rd, it's the full day. So far, we have Stephen Wolfram who will be joining. We have Kurt Mungle from Theories of Everything. We have Albert Nirenberg, the hypnotist, who some of you will also know. And a couple other surprise people who will be announced shortly. And it's going to be a really fascinating time. It's basically the whole day. And we'll have a good chunk, actually a significant chunk of time dedicated towards research and project exhibits. So, if you're working on a research paper or an idea or just kind of an engineering project or anything like that, please feel free to come to the event. If you need, we can, you'll basically have an interesting audience of people to expose us all to. We'll have some of the most interesting, researchers, investors, donors, builders, in Cambridge and Boston, the university system there, but also a lot of people are coming from elsewhere in North America and around the world. It's that kind of big of an event. And I think these are really good experiences, not just for connecting and finding collaborators, but you also, because there's so much diversity of what people are exploring, is you get a lot of cross-pollination. So one of the ways I'm thinking of even physically setting up the space is like, how can we connect everything and organize them so that you get a lot of cross-pollination between different fields and ideas. So we'll have people in physics, mathematics, theoretical neuroscience and cognitive augmentation, artists, musicians. We have a whole mix. I guess the one thing is that we want people to be pretty, we want a bit of rigor. We want people to be rigorous about it. But yes, Morgan, Frontier Tower is definitely on the list. I got to stop there at some point. But I'm going to put the link for everyone in the description if they want to come. Once again, it's August 23rd. If you're going to come, you can just stay for the day. I would also suggest staying Friday and Sunday because I am planning a couple other things on those days as well if you're able to. But at the very least, just make it on Saturday, August 23rd. What I'm going to do right now is I'm going to put the link to the main event page that you can sign up on Luma. You can get tickets for it, and then the separate page if you want to exhibit your research. Okay, so here is the main event page, the Luma page. And, if anybody needs help with anything on the financial end, if you really, really need help with tickets or flights or something or housing, just shoot me a message. Can't promise anything. It's sort of on a rolling basis, but if you really, really need help, we'll at least try to figure out something to get you there. So there's that. And then the other link that I'm going to send as well, the Google Forms, the application link for exhibitors. Pretty straightforward, simple application. As for what you guys will be showing, so, if you have a startup, you can demo your startup, you can do all that kind of stuff. But you can also, if you want, you can follow sort of the traditional research conference format where you kind of have a poster board with all your information. So you'll have to provide your own poster board. But if you really, really, really need help with the poster, reach out and we may be able to cover that for you. And the separate option as well with your posters or whatever is feel free to get creative with it. If you don't want to just put squiggles and words on a white poster board, you can get a little more creative with how you design it. I believe you're going to have people kind of per table with their own poster boards and everything. All right, cool. Jay, we want to see you there for that. It's augmentation. It's right up your alley.
Great. Looking forward, man.
Perfect. All right, y'all. I'll catch everyone next time. Hopefully tomorrow and day after for the next two salons, because I think after that there might be a slight break. And hopefully this will be up on Jay's channel, which you should all subscribe to when he makes it. So okay, cool. All right, thank you again as always, and we'll see you soon. Peace,
Thank
everyone.
you.
Take care, everybody.